Can you all see the screen? Right. Maintaining circular motion. Maintaining circular motion. How the circular motion is maintained. So that is what we are going to discuss. Right. Uh, Now remember, when an object is moving in a circular motion, for example, it is moving in a circular motion around this axis. Now remember, uh, it is not in equilibrium. It is not in equilibrium means even though we feel like it is moving at constant linear velocity, the direction of the linear velocity is always changing, right? This velocity is always changing towards the center of the circle. So that is what we call centripetal acceleration. Right? There is an acceleration. Why? This velocity is always changing. When the direction is changing, even though the magnitude is not changing. For example, same object over here, right? It is having the velocity up to this direction. So velocity is always changing. The direction of the velocity is changing. So it is a vector scale. So therefore, it is actually towards the center of the circle. So that is what we have derived that day, right? That acceleration, centripetal acceleration is equal to r omega squared, right? The square of the angular velocity, even though the angular velocity is constant, when it comes to the linear velocity, there is an acceleration towards the center, not because of the change in what? Magnitude, even though the magnitude is maintained constant, remember the direction is always change to the center of the circle, right? Okay. Now remember, if there's an acceleration, it means what? There must be an unbalanced force towards the center of this circle, right? Okay. So it means when an object is in circular motion, there must be to have this object pulled into the center. It is not in equilibrium, remember. This is not in equilibrium. Right? If it is in equilibrium, it means balance of forces. There is an unbalanced force acting on the object. It is not in equilibrium. Keep that in mind. That is why there is an acceleration. If there is an acceleration, so actually this is a hidden force, right? This is a hidden force, but we can feel. For example, when we are in a vehicle, when the vehicle is taking a bend, we can feel there's a certain force acting towards us. That is why we go unbalanced, right? So that force is what? Centripetal force. Centripetal force, right? Centripetal force. So this unbalanced force is called the centripetal force, right? So centripetal force is the force that is keep the object uh, pulled towards the center. That is why this object is. Otherwise, if you do not have this force on the object, right, this object would what will happen? This object will take a this route, right? Okay. Uh, right, it will take this path, right? Okay. So this object is not taking this part because this object is constantly being pulled towards the center of this orbit, right? It is called a centripetal force, right? Okay, so it means you can apply same equations we have applied in linear motion, right? F equals ma. Same equations can be applied, right? The formulas may be different, but still same principles can be applied in linear motion also, right? All right. So what is centripetal force? If they ask you what the definition is, right? It's a resultant force. The resultant force towards the center of the circle required to keep a body of uniform circular motion. Circular motion. It's the resultant force. Resultant force means unbalanced force on the object toward the center of the circle required to keep a body of required to keep a body in uniform circular motion, right? Not off. In uniform circular motion. In uniform circular motion, right? Okay. That is the force that is keeping the object on uniform circular motion. So it's a perfect circle, right? Mathematical circle, right? Now it is always directed at the center of the orbit. Right? Always directed at the center of the body's rotation. Body's rotation. Always directed towards the center of the body's rotation. Now if we have a person here, right? Now here it is on a string. On a string. He is rotating this object around his body. So it is what? The centripetal force is what? This force. This is the centripetal force. Right? So now the centripetal force is actually what? The tension on the string. Right? The tension in the string is the centripetal force. Centripetal force is the tension. It's the tension of the string. Centripetal force is the tension of the string. Right? Okay. Now remember now, centripetal force and the centripetal acceleration having the same direction, right? Force is to the center, therefore the centripetal acceleration is also towards the center, right? Now Why is that? This is due to the uh, second law of Newton, F equals ma, right? There's an unbalanced force towards the center of the circle, so therefore there's an acceleration. What is this acceleration? This acceleration means the direction of the linear velocity. Direction is always changing. That is the acceleration, right? Not with the magnitude of the velocity, but with the direction of the velocity towards the center. That is what is we call acceleration towards the center, right? Okay. Now, when it comes centripetal force, right? Now, there's no actual force called centripetal force, right? Why? This centripetal force can be any force. Any force acting toward the center can be taken as the centripetal force. Otherwise, there is no any special force called centripetal force. Now, here in this example, the tension needs the centripetal force. Here, the tension, right? When a vehicle is taking a bend, for example, now racing vehicle is taking a bend, Formula One car. So, in that case, centripetal force is the friction on the tire, right? The friction needs the centripetal force, right? So just like that, any force can be taken in the form of a centripetal force. Any force can act as a centripetal force based on the situation. I hope it is clear, right? Okay. Now, one another good example. If we have solar system, I'm asking from you now. If this is sun and the Earth is orbiting around it, right? Now, in that case, on Earth also there is a centripetal force. Now, in that case, which force is acting as the centripetal force on Earth? What is that force? Yeah. What is the force, centripetal force, acting on Earth to rotate or orbit around the Sun? Yeah. What is the centripetal force? Hello? Any answers? No. It's a gravitational pull, right? The gravity. That they are the gravity between these two objects, right? The gravity is acting as a centripetal force. The gravitational force, right? The gravitational force is the centripetal force acting between the sun and the earth. Now here we have earth. Okay. Now again, let's further discuss on this topic, right? Let's put some equations and write further discuss on this. Okay. Centripetal force. Now we can apply plug in the formulas. Now if we can remember last time we have derived the centripetal acceleration and we came up with this equation F equals mv squared r, or v squared r means what? V means r squared omega squared. R squared omega squared divided by r, you are getting it as what? M r omega squared. Right? So again we can tell r omega separately. M r v. M r omega, sorry. M uh, v. R omega can be written as v. Again omega. So the force can be represented in any of these three formulas. Right? So you don't need to memorize everything. If you know only one formula, with that you can derive other formulas. No need to memorize all. If you know only one formula, other things you can derive based on the question. Sometimes they may ask you about the linear velocity, mass, radius, angular velocity. So based on the question that is being asked, you should decide which formula to be used, right? So omega means the angular velocity, linear velocity, the mass of the object, F is the centripetal force, right? The units should be the SI units, rads per second, meters per second. Here, mass is given as kilograms. Now again, I am going giving you this as a diagram. Okay, this is our object. There's a force. Centripetal force is this. Linear velocity is this, and it is at omega. Uh, Angular velocity, it is constantly rotating, and the radius is also important. Without radius, you don't know the value of velocity, linear velocity. Linear velocity depends on the radius. Why? R omega is equal to velocity. This force means centripetal force. Right? So the resultant force, or the unbalanced force, acting on an object rotating along a point or an axis. Right? Right. Uh, Now let's take a object or a ball. Let's say just like in a question. Uh, right. Now this is a question. Now there's a string, right? And this it is being rotated around the is the orbit, and this object now it is rotating not horizontally, vertically being rotated. This object is having a mass of m, gravity is g, right? You can take gravity as g, and there's a tension on the string, right? This is T1, right? Now same object, and when this object is over here, same mass, there's a tension. The tension is now different. T2. So practically think. When you are rotating a object on a string, your fingers can feel the tension. When do you feel the T max, highest tension? The tension changes, T2. And at the bottom again, the direction of the tension is to the up. Tension is also now different value. Object is M, right? And over here again, tension is this on the object. Still the mass is there, right? Now remember, gravity is always towards this, right? Now before moving on to the next part, I am going to give you a task. Let's see whether you can apply this. This is the most important part. In questions, this is being tested. I am using this information M, G, T1, T2, T3, and T4. Right? I want you to give separate formulas for T1, T2, T3, and T4. And let's imagine it is being okay. Yeah. Uh, it is being rotated at constant velocity. Right? Uh, Radius of this rope is R, and it is being rotated at constant angular velocity omega. Right? Now using this information, R, omega, M and G, where it is appropriate, I want you to give me formulas by applying the Newton's second law. Right? Give me formulas for T1, T2, T3 and T4. Can you do that? Using these values only. If you can do it, actually you have actually done a great job. You have understood one of the main areas. Right? Gravitation is G. Can you do it? Right? Let's see whether you can do it. Okay. Hello.
Okay.
Right. As you can see here, uh, let's start off with T1. Now again, T1 is towards the center, right? So when we apply, if it was MA, T1 is the unbalanced force, and also we have gravity, right? Weight is also acting on that. So T plus G, same direction, equals, this is the overall force, no other force is acting on that, and M is the mass, R omega squared is what? It's acceleration, R omega squared, right? So you can make T1 the subject, T1 equals M, you can make it into a bracket, R omega squared minus G, right? So that is the tension. So remember now, because of this gravity, gravity and the tension is acting together. So at this place, to maintain this acceleration, you only need a little amount of tension. So when the object is at the top, the T1 value is a little value. Why? To maintain this acceleration. Same acceleration is there no? Everywhere. Why? Object is rotating at the same angular velocity and the radius is all the same. So mr omega square. So everywhere same centrifugal force is there. Same centripetal force is made by combining these two. So therefore, since the gravity is there, you need only a very little amount of tension to have this acceleration. So at the top, you have the least acceleration. Let's go with the sides. Now remember when you go to the side, the mass or the weight is towards here, this side, running parallelly. So therefore, it is not directed towards the center, right? Because it is there, what? Perpendicular to the center, right? Perpendicular to the centripetal force. So therefore, we can neglect it. This is not affecting on the centripetal force. On the centripetal force, this is not acting. So again, so it means only T1 tension is there acting on that. So T2 force is the only force, only unbalanced force at the center of the orbit. So therefore T2 equals again mr omega square, rotating at the same velocity, right? So we can take T2 as the least, T2 as the maximum tension, is it? Right? Still too early to decide. Let's go with T3. When you get T3, remember uh, the gravity is acting against the centripetal force, right? Here. So it means to maintain, so out of this tension, certain part is being deducted by the mg. So therefore, you will have to have a greater tension to maintain the same acceleration. So at T3 must be a larger value. Why? To maintain the same acceleration, centripetal acceleration, you will need a bigger tension. Let's see. T3, applying the equation minus mg equals again same centripetal acceleration. So when you make T3 the subject, T3 equals, we can take here into the bracket G plus R omega squared. See, now out of these three again, T3 is the largest. Why? It should compensate the weight of the object force. So when we are rotating a object with a string in a vertical plane, when the object is at the bottom over here, you have a greatest tension if you want to maintain the constant angular velocity. Remember, that is the assumption. It is rotating at a constant angular momentum. So therefore, there is a greater risk of the string being broken at this place. If it is getting broken, this is the place where it will get broken by, because you have a greater tension on the string. So again T4, not much difference, same as 2T, right here. Again the gravity is to this direction. So therefore only T4 is there on the object. So again T4 is equal to mr omega square, right? So it means T4 and T2 are the same. T4 and the T2 are the same. And between all three, Greatest is this. T3 is the greatest. T1 is the least. These two are in between. So now, based on this phenomena, they may ask you questions differently. MCQs, structured essays, right? But nothing to memorize here. Just understand what is going on here, right? Now I will give you a question. Again, there's an object and it is orbiting around this. The length is what? The radius is zero point 0.5 meters. The mass of this object is 8.0 kilograms, right? Actually, it's a bucket, right? It's a bucket filled with water, right? And the bucket is tied to a string, and it is orbiting at a radius of zero point 0.5 meters, right? I want you to find minimum speed, minimum speed needed. Keep the water in the bucket. Keep the water in the bucket. Right. You have to find the minimum speed of the bucket you must maintain to keep the water in the bucket. Right. So you should decide. Now this bucket is rotating around. To which place you must plug in the formulas. Whether the bucket is here, you find the minimum velocity you need. Either the bucket is over here, you need to find the minimum velocity required, or either the bucket when it is over here. So it means minimum velocity must be found when the bucket is here or here or here. You should decide on that, right? If the bucket, if the water can stay inside at a particular place, when the bucket is at a particular place, the water is still inside. If the water is still inside when the bucket is over there, it means around the whole circle still the water will be inside. So you should find where do you have the maximum risk, right, for the water to spill over. So at that place, you must maintain at least a certain velocity. A certain velocity, at least certain velocity. So we are asking the minimum velocity. If you rotate the bucket less than that velocity, water will spill. So out of this position, you have to find where is that highest risk is there. You decide. So to that place, you at least to overcome or to stop water from coming out at the highest risk place, you must have at least that velocity. Keep that in mind. Plug in the formulas at the right place where the maximum risk is. At the maximum risk position, the minimum velocity, at least that velocity you must maintain. What is that velocity? So everything you need is given, right? Uh, okay, fine. Now here's the catch. The maximum risk is over here. So let's plug in the values. So remember, the tension is there, right? Okay. Tension plus the total mass, including the bucket and the water, mg is equal to mv square divided by r. Now remember, we are asking the velocity minimum. When the velocity for the velocity will be minimum, right? Velocity will be minimum when the, now this is force, no? Addition of these two is the centripetal force. Now when the applied force is minimum, the velocity will be minimum. Applied centripetal force is minimum, the velocity will be minimum, right? And the m value we can't change. Now here, now we can, it means we can, to have the minimum velocity here, we have to have the minimum force. Two, we should reduce the force as much as possible. Now the thing is, mg cannot be changed. It's what? It's a gravity now. We can't reduce mg. It's a constant value. Only variable we can minimize is tension, right? So to obtain minimum velocity here, we must have the minimum tension, T minimum. T minimum means what? When the tension is zero, you can't go beyond that. No? Tension is always to here, not the other direction. No? When the tension is minimum, you have the velocity minimum. So therefore, it means, so now at this place, when the zero tension is there, you have the minimum velocity, right? So now let's plug in the values, right? There's no tension, m10 will get cancelled off, right? Then we have only v squared, v equals r g square root. So you can take any value you like for g. Let's say if I'm taking for my, since it is easier for me to apply, if I ask, right, 10 as the gravity, radius as 0.5, square root of 5, approximately around 2.2 meters per second. So you should know how to plug in your, apply your physics. Understand what is going on. Very easy. Physics is the easiest. Out of all three, chemistry, physics and biology, physics is the easiest. But you should know when to understand. Until you understand, don't give up on the concept. So that is, so you don't need to study again, right? Just like chemistry. No need to study and go back and forth with the notes. The moment it is being taught, spend some time with it and try to understand itself, right? When the theory is done on a particular week, make sure to fully understand it. Once you fully understand it, after doing question, you will never forget it. It will be there for your lifetime, right? That is the nature. So you need a bit of practice, past paper question. Very interesting, right? Okay, right. Uh, okay. Now actually, we have completed the further mechanics. All the mechanical parts are done. We have now actually we are moving on to So after centripetal force, we are now moving on to electrical fields, right? A new chapter, uh, right under field and particles, right? So in the A2s, we are moving on to electrical fields. And so we are done with the mechanics part. Uh, okay, now we are in electrical fields, right? Now under electrical fields, electric fields, we have defining on electric field, on electric field, electric field strength, electric force between two charges, electric field potential, field and potential, electric field between parallel plates, parallel field plates, electric potential for radial field, electric potential for a radial field representing radial and uniform electric fields. These are the topics, right? Let us move on to electric fields and defining electric fields. Okay. Uh, okay. Okay. All right. Um, so electric field is defined as a region of space in which a charge particle experiences a force, right? An electric field is a region of space in which a charged particle experiences a force, right? Um, Now, if you have a particle, a charged particle, let's say positive particle, when it is in the space, for some reason, suddenly it is feeling a force on it, unbalanced force. So at the beginning, scientists didn't know what that force was, but they felt it. There's a force. There's a force on this particle because it is charged, right? Uh, as a kind of supernatural, unknown, hidden forces there on the particle. Now remember, in the other forces, you can see friction, you can feel because the two surfaces are moving against each other, so you can feel the friction. You know why there's friction, right? Tension also, you know why there's tension. But here suddenly, without any for any visual there's no evidence, but there's a force on you, right? Just imagine now when they first felt it, right? So the first felt it means even before the advancement of physics and the pre-industrial revolution times also, people must have felt it, right? Even during the uh, pre-industrial revolution, mean during the dark ages, I mean even the era of kings and queens, during that time also they must have felt it. Static electricity, attractions, they must have felt. But they must have felt it. But there's no visual evidence for it. So must be they must have felt kind of supernatural, right? Why suddenly with no visual evidence, there's a force on you. You can feel, but there's no way to explain. Now later, now after industrial revolution, and then now we know, this is part of science. So there's a force on you because there's an invisible field, right? When it is in an invisible electric field, there's a force on the particle, right? So now why he is feeling a force? Why? Because there's a invisible field, invisible mesh, right? So we are calling it as in the background. In its background, there's a force field, right? Uh, and in the background, there's an electric field. There's a field. Because of that field, to a charged particle, there's a force. Now, these type of forces are called Force field. A force on a charged particle by a field. A force on an object by a field. That field is most of the time invisible. Force field. Unlike friction, tension, right? So even gravity, as for Newtonian physics, gravity also something like this because of the gravitational field, right? In the fabric of time and space, right? The fabric of time and space is being warped due to the mass. So therefore, you have gravitational pull on you. So gravity is also there because of the field, right? Okay. Uh, right. I hope it is clear. It's a force field. Now, if a particle is having a charge, right? It could be either just like a normal particle, normal object. It could be stationary or just like any other object. It could be moving, either moving or either stationary, right? Okay. Uh, Another thing is this part. If this particle is in a field, right? If this charge particle is in an electric field, or if this particle is in a field, this particle can feel a force on it, right? Whether it is stationary or moving, it may feel a force, will experience a electric force because it has a charge. Because of having a charge, whether it is stationary or moving, it will have a on that will have a force. It is called electric force. So electric force is a force field, right? Okay. It is starting to feel electric forces. Right? Now remember, not just when it is in a field, on that object there's a force. Since it is has a charge, when it is in the field, it is having a force on it. Not only that, when a particle is charged, the charged particles are exerting a force on its own. It has a own field also. Right? Charged particles they have its their own electric field. Right? Charged particles have its own. It is also having a electric field. It is also making the electric field around it. Charged particles have a electric field itself. Right? Okay. Now, because of that reason, when a charged particle is in an area, you have a field. If you keep the charged particle on a area where you have a background field, the charge on that charge particle, you are going to have force. And not only that, if you have two charge particles, let's say positive and negative, now I told you these particles are also making a field, its own field, electric field. Because of these electric fields, it is making a force on the neighboring particle. For example, this positive particle, positive object is here, and it is making an electric field in the background. Background electric field. It is creating background electric field. Now this charge particle, because of its charge, this background electric field created by the positive charge is creating a force on this particle, right? Because of the electric field created by the other particle in the background, on this particle there's a force, unbalanced force, electric force. Same thing happens other way around. Because of this particle is also making a field. Because of the field created in the background by this particle is starting to feel a force created by this electric field. So it means they are creating electrical field on each other. Therefore, because of they are being charged, there is an unbalanced force control. And so it lacks, since they are oppositely charged. For this force created is created in opposite directions. So therefore we feel like they are being attracted to each other, right? They are being attracted. Why? The forces, electrical forces are acting on opposite directions. So they are being attracted. Right? Electrical force. Let's say there are two particles oppositely charged. They are in the distance. They are being kept at distance of r distance. Right? Oppositely charged particles. Now, if the particles are oppositely charged, say similar between positives and positives, you know these things, right? They are repelling each other, right? Forces are in opposite directions. So we feel like they are being repelled. Negative, negative is also same. Repel. Because of the electric field created on against or on each other's charge. Again, they are repulsive. So all these attractions and repulsions are due to the electric field they have created because of the presence of a charge. So if an object is having a charge, they have an electric field they have created, and in the presence of a electric field created by another object on that particle,